Hi everybody, welcome back to Edge the DWF channel. This is the last video of a series started a few years ago when I decided to try making my own vector monitor using the CRT and other suitable parts from this old 11 inches black and white TV that was left for dead. If you haven't already watched the other videos, I suggest you to pause this one now and catch up with what has been done and explained previously. Otherwise, you could be missing quite a lot, just like this poor old TV now. Links are in this video description. The circuits shown in this video produce dangerous voltages and are not intended for untrained and unexperienced persons. This is the vector monitor block diagram that I have also shown in all the previous videos, indicating which particular block each video was focused on. The first new circuit that I'm going to show in this last video is the cathode driver, which on a black and white monitor is just a single one, not three separate ones for red, green and blue as shown in this image. The second one is the so-called spot killer circuit that checks the presence of correct XY deflection and in case of a failure cuts the electron beam in a fraction of a second to avoid phosphor burns in the CRT. However, as the new circuits were added and tested, I've realized that the older blocks still needed some tweaking and small changes. Before I started building the new circuits, I decided it was time to mount the CRT and all the circuit parts into a suitable rigid chassis, so I started building it using pieces of old black and white chassis that were almost always built inside robust steel frames. The XY deflection circuit has been placed on one side of the CRT. And the CRT supply has been placed on the other side, but I may decide to relocate it in a different place in the future to have a better access to the trimmers. In the previous video we have seen how to move the electron beam across the CRT screen surface, but so far that was always with a fixed beam intensity. Now we want to vary the beam intensity to draw objects with different brightness levels and to completely extinguish the beam during movements needed to jump from one object to the next being drawn. Now, on every CRT, the beam intensity for any fixed set of anode and G2 voltages only depends on the difference between the voltages of the G1 electrode and the cathode. The lower this voltage difference, the brighter the image that will result. In any case, however, G1 must be always at a lower voltage respected to the cathode. As soon as I had some working deflection, I started taking notice of some useful voltage difference, because I was going to run the CRT at different anode and G2 voltages than the ones suggested in its datasheet. At the time, I didn't have any cathode drive circuit, so the cathode was simply grounded through a resistor, and the G1 voltage varied with a potentiometer from the ground level down to about minus 50 volts. In this picture, the grid voltage is at minus 26.2 volts and no image appears on the screen. So, for any voltage difference higher of about 26 volts, the beam is completely cut off. By bringing G1 at minus 22.5 volts, so reducing its voltage difference with respect to the cathode, we already have a bright trace. Further reducing the voltage difference gives a much brighter beam, so let's say that a suitable cathode drive circuit must be able to swing its voltage on an interval of about 10 volts. Another thing we want to measure is the actual beam current to have a good idea about an upper boundary for this current. In this case, the multimeter is connected between the cathode and ground, measuring the current flowing at different brightness levels. In this picture, the trace is already clearly visible with about 15 nanoamperes. With a bit less than 500 nanoamperes, the trace is already quite bright. This is already very bright, and the bin current is 1.6 microamperes. Let's say that 10 microamperes gives a trace much brighter than it's even needed. I can then use a few milliamperes to generate the cathode voltage drive, and since the bin current will be subtracted from it, I can be sure that it won't affect the actual drive voltage. So here is the circuit I'm going to build. Transistors Q301 and Q302 form a cascode pair. The lower transistor will sink a variable current proportional to the input brightness signal. The input signal will be at 0 volts for a completely cut off beam, and in fact Q301 will be off with 0 volts on its base. The total emitter resistance on Q301, that can be varied, sets the current level. So for the maximum input voltage we can have from a minimum of about 6 milliamperes to a maximum of about 16 milliamperes. C303 will speed up the brightness changes. Q302 is a high voltage transistor, even if on a small CRT like this it will never see more than about 85 volts on its collector. But I happen to have many spares of this kind. It will turn the current sunk by Q301 into a voltage drop on R314, which will drive the cathode of the CRT. The higher the current, the lower the collector voltage going to the cathode, so the brighter the beam will be. Now, as it's usual on a cascode circuit, the upper transistor base is fixed to a stable DC voltage, and I have done that with a rather large circuit. This is a key part of the spot killer circuit. First of all, if this DC voltage goes to 0, Q302 will be off and no more pass any current, so the cathode voltage will sit at the maximum voltage and no trace will appear on screen. This base bias is generated only when both the two supply rails plus 12 and minus 12 volts needed for the XY deflection board are present, and the base bias is removed as soon as the first of them fades away during the power off phase. The red LED is just there to indicate that both supply rails are present. The 5V Zener diode in series with the green LED will set the DC base bias to about 7V. This voltage needs to be higher than the maximum voltage we can expect on the Z input. This input is never supposed to reach more than 4 or 5V, so 7V is a safe value. We also don't want to exceed too much the safe level to allow Q301 to work with a low collector voltage and dissipate the least amount of power possible. C302 will filter any residual noise on the DC base bias, and R310 will help discharging C302 as soon as the base bias is removed. KV voltage is generated by the CRT power supply and is about 80 to 85 volts. D303 and C301 will hold the full input voltage when the monitor is turned off and Q302 base bias is removed. With this circuit in place, I should already have a working monitor with proper brightness control and be able to turn it off safely without the risk of getting a very bright spot somewhere in the screen surface. I've then quickly assembled the circuit into a piece of perf board. I want to quickly test the base bias circuit, so only plus and minus 12 volts and of course the ground wire are connected. Both LEDs are glowing when both the supply voltages are present. Now let's remove, for example, the plus 12 wire. Okay, both LEDs go off. Let's try now with the minus 12 wire. And it seems all is looking good so far. So far so good. I had then added a plastic layer on the back of the PCB and mounted the new board on the monitor's frame. Initially, I run the monitor with the NEC PCB disconnected, looking at the cathode drive waveform on the oscilloscope. Well, this really looks good. On the bottom trace we have the Z input from the GAN PCB, and the upper trace is the cathode drive. The output is inverted and starts from around 76 volt for the blank level. Of course, I can change the cathode drive depth with the contrast trimmer. However, I believe the voltage is still a bit too high. Now I've connected everything. We can hear some typical vector noise. But I can't really get an image, no matter how I set the brightness and the contrast. As I suspected, the cathode to G1 voltage difference is still too high. We needed about 20 to 30 volts, and we are at more than 40 volts, since the G1 voltage can reach 0 volts maximum, which is the level in the middle of a scope screen here. So, what options we have to translate the cathode drive down to about the 20 to 30 volts level? Well, actually, there are a few different ways to do that. The first, but probably the worst option, would be adding a resistor and Zener diode on the cathode voltage input, let's say 33 volts. But the Zener will need to run at a current higher than the maximum drive current. So in this case, let's say we could get away with 20 mA. This means the Zener will need to be rated at least to 1 watt. Well, there are better ways, I'm sure. We could instead add a Zener of around 22 volts in series to the cathode voltage, so subtracting the Zener voltage from the supply voltage. In this case, the Zener could be rated for only half a watt and dissipate power only when visible parts are drawn. This is already a much better solution, but it still has some drawbacks. In practice, the actual Zener voltage would vary both with the actual current being drawn and the diode temperature. So I really want to find another fix, even if the one shown here could be working very well in practice. I've decided instead to change the G1 brightness control like this. I have added R201 going to the cathode voltage supply. Previously that side of R201 was going to ground. In this way, G1 can be brought to a positive voltage closer to the cathode voltage. A positive voltage on G1 seems not allowed by the datasheet, but I'm sure it will be fine as long as the cathode is kept to a higher voltage like in this case. Let's try again with the G1 mode. I'm bringing slowly up the brightness. Look at that! Isn't that awesome? Wow, finally! Well, geometry and linearity are quite wrong anyway. Let's see if the contrast works. Yes, it seems so. By the way, the lines are sharp and focused, but the camera seems not coping with the brightness levels. Now it's really time to complete the spot killer circuit before I start playing with geometry and linearity issues, as I have no replacement for this CRT. As you have seen in part 4 video, I have used this Müller deflection board that was designed for the Vectrex console CRT. This circuit has been really modified to allow a higher output current needed for my CRT yoke. Now the circuit has this unblank output suitable for the Vectrex Z amplifier, but I'm not really going to use this one, first because it senses only the X deflection, but I want to check for the correct presence of both X and Y deflections. The second reason is that sensing the yoke input drive in that point of the circuit could still produce a valid unblank voltage when, for example, the yoke gets disconnected, since in that case the driver would still produce an output voltage alternating between the two supply rails. I'm going instead to check the presence of an alternating voltage on both the X and Y current sense resistors. These resistors will develop a voltage drop only if the yoke is driven unconnected. But first I need to see how this sense voltage looks like. This is the X deflection sense. It peaks to plus and minus 1 volt. And the most important fact is that deflection only happens for about 5 milliseconds after 10 milliseconds intervals with no deflection. This instead is the Y deflection current sense. It peaks to just less than plus and minus 2 volts, since my vertical yoke has a low inductance and needs about 1.6 amperes of current for full deflection. So I have designed this simple circuit. The X and Y current sense voltages are rectified and doubled with a 2-diode and 2 capacitors voltage doubler. The series resistor with different values accounts for the different voltages I have from the X and Y deflections. The 150 kΩ resistor discharges the rectified DC voltage with a time constant of about 70 milliseconds. This is rather long, but remember that the gate PCB draws one complete image during a 5 milliseconds interval, then the deflection output remains idle for twice that time, so the rectified voltage must not decay too soon or the spot killer circuit will trigger at every idle interval. Then I created a stable voltage reference with a simple silicon diode and a voltage divider. The output voltage out of the divider is in this case about 0.45 volts, but probably even a 0.55 volt divider would be okay, giving a slightly faster reaction. The two rectified DC voltages and the reference voltage go to a dual comparator integrated circuit. It will ground one or both its output pins if one or both the rectified DC voltages drop below the reference voltage. The outputs are open collectors, so they can be simply tied together. If the output is grounded, it will ground the upper transistor base of the cathode driver circuit, cutting off the electron beam. If this circuit is triggered, the red LED will still be glowing, but the green LED will stay off. Of course, I have experimented with the voltage doubler values to fine-tune the components before building the final circuit. This is the X deflection DC output. And here the Y deflection. I could even increase the series resistor a little bit. At this point I have added the spot killer circuit on the cathode drive perf board PCB. Here it is in action, only the red LED is on. But just because I haven't connected the sense wires yet. And of course there is no image on screen. Now I've soldered the two wires. Both LEDs are now on. And the cathode drive works normally. As a final test, I must have the courage to remove one deflection input with the monitor on. First, let's understand what exactly are the geometry and linearity issues. Here I'm now looping a video fragment. just observe the UFO as it travels from the center part of the screen to the left. Notice how its dimensions change as it moves. Notice how it shrinks, especially on the horizontal dimension. These kind of issues depend on the incorrect gain setting on the XY deflection amplifier, and especially incorrect settings of the so-called predistortion circuit that we are going to see soon. Geometry issues are instead the uneven corner sizes and positions, and the perimeter lines not straight. These are more related to a set of little magnets that are placed around the deflection yoke and that need to be rotated to correct the geometry. Initially, I tried tweaking all the magnets, then the yoke position and the image centering rings. But a couple of hours later, nothing had really improved. I decided then that I would first try to solve the linearity issues, since the geometry issues could be getting worse also because of the wrong deflection sides on the screen borders. So let's examine a typical arcade vector monitor deflection input circuit. This one is taken from the Italian Antarex MTRV schematic, but the circuit is identical to electro-home monitor used on the original Atari cabinets. The input signal first goes into a variable resistor that more or less sets the overall deflection depth. I say more or less because, in reality, all the input settings will interact with each other. Luckily, there are some guidelines to properly set them if needed. The other side of this input variable resistor goes to this funny circuit, which is called the predistortion circuit. It's a really clever but simple circuit. First of all, the diode bridge makes the TR13 collector always connected to the most positive voltage, which is the input side for a positive deflection signal or ground for a negative deflection signal. Similarly, TR13 emitter will be always connected to the most negative voltage. TR13 itself makes a constant voltage clamp where the voltage can be varied with RV3. This circuit, however, will start working when the input deflection signal gets higher than 2 diode drops due to diode bridge plus the clamp voltage. So, for input voltages less than this clamp plus bridge voltage, the low side of RV4 is in practice floating. Instead, for higher deflection voltages, it will become an additional attenuator. This makes the size of actual deflection voltage decrease near the border of the screen to counteract the natural distortion caused from the fact that the actual phosphor screen is flat and not really a sphere sector. So, near the edges, the same angular speed will result in faster linear speed. This is the analogous of the north-south, east and west correction mechanism on the raster deflection systems. Let's examine now the input part of the XY deflection circuit that I have used. Here we have first a fixed attenuation of about 1/11. Then we have another fixed attenuation that kicks in when the previously attenuated input signal starts to be higher than 1 diode drop. This predistortion circuit has a different bottom resistor value for X and Y axis. Now, this was a fun circuit for the particular Vectrex CRT, but I obviously want to make it tunable to find the correct settings for my 11 inches CRT. So I will modify the X and Y input circuits like this. The first input attenuator will be made variable by substituting the fixed 100 ohms resistor with a 47 ohm resistor in series with a 100 ohms trimmer. And the predistortion attenuator will also be made variable by substituting the fixed low side resistor with a 1 kilo ohm fixed resistor in series with a 10 kilo ohms trimmer. So I've quickly applied these modifications to my deflection board, as you can see in this picture. Before testing this modification, however, I also decided to remove all the yoke magnets to first try to come as close as possible with only the deflection input settings. The gain PCB has then been set for the nominal plus and minus 10 volts peak deflection on the x-axis, and plus and minus 7.5 volts on the y-axis. Basically now I will iterate this process. First, I'll set the overall attenuation to fill most of the screen area. Then checking the deflection amplitude at the center of the screen and comparing it to the amplitude at the edge on the same axis. Using the predistortion trimmer, I'll try to make the edge amplitude as close as possible to the center one. This needs to be done for both x and y axes, and then check the overall deflection depth and start over from the beginning a few times. Then we observe an object moving from side to side to see if it seems to shrink or expand. At this point, I have installed the back of the yoke magnets and started finding their best orientation to adjust the corner positions and the border edges. Every magnet position will interact with all others. Of course, after finding a good compromise, I had to tweak again all the deflection input settings. However, the geometry is not perfect, probably because the yoke rewinding was not perfectly made either. A few iterations later, the gain field looks very good. However, having found an acceptable result, I've added a few drops of glue on the magnets to hold them in their new position. In the end, I'm very satisfied about the overall result. The monitor image quality is hard to capture in the videos and pictures. Here, for example, the only focusing artifacts have been added by the smartphone camera. This has been a very long project, but I've learned a lot from it. I hope it was interesting and fun for you as it has been for me. If you have any question, please use the comment section below. It's all for now. Have a nice time and thank you for watching.